On this periodic table, we're going to color in all the elements that are on the zigzag line, which separates the metals and the non-metals. So let's do that one. This one. Now, don't get excited and start just doing them all. Give me a moment. Germanium, antimony. Here we go. Here we go. Palladium from Poland. That's what it's named after. Okay, so those are all what we consider to be on the zigzag line. Now, the zigzag line also not only separates the metals from the non-metals, but they are all called metalloids. Now, I did not do this one, aluminum. Miss Munson, he's touching the zigzag line at the top and on the side. So shouldn't we also? No, we're not. We're not going to, because he's not a metalloid. Aluminum, even though he's on, so in red, even though he's touching the zigzag line, which is right here, do you see that? It should have been on your notes. It's probably like darkened, like a dark line. Even though aluminum is a dark line, we still do not consider aluminum to be a metalloid. He is still just considered to be a metal only, okay? Not a metalloid. So that's the reason why I want to make sure that we all know that. Why? Because there's just always exceptions to the rules. You know, I know there's rules that we have in science, but for some reason, especially chemistry, there is always one or two exceptions to it. And this is an exception to one of the rules. All right, let's go back to our notes and let's keep going. Now let's talk about those metals and non-metals that are separated by the zigzag line. Now, the metals, most of them are solids, and I say most, at room temperature. They're shiny and good thermal conductors and good electrical conductors. So they transfer heat very well as electricity. They have very loose electrons that jump off of them very easily, so that way they can become stable, and that causes metals to be cations. Oh, that's important. Not only is that important for this unit, that is important to know for like most of the next units. Cations. Because when we do bonding, we need to know that. Alrighty. Now, why are metals such good thermal or good electrical conductors? Well, because their electrons are so loose, their valence electrons are so loose and they come off so easily. Those valence electrons are the valence electrons that are moving through that wire for electricity. Okay, that's the reason why. Next one, nonmetals, which are pretty much on the right side of the periodic table. Solid, liquid, gases at room temperature. They can be either one. Okay, now they are very poor conductors of heat and electricity, and they need to gain electrons to become stable. And when they gain those electrons, then we call them anions. Okay, so nonmetals are pretty much going to be anions because they are going to gain electrons to become stable. Metals lose electrons to become stable. Let's keep going. Those metalloids that are on the zigzag line, except for aluminum, it says here, are found along and on either side of that zigzag line, except, look at that, there's an exception to the rule I told you, aluminum, right? He is still going to be a metal. Some, they have some properties of metals, and they have some properties of non-metals. Okay, they have both properties. Yeah, crazy. Let's keep going. Now, let's go ahead and talk about a little bit more of the periodic tables, but we're going to talk about groups. Okay, and how each one's a little different. Group 1. Group 1 are what we call the alkaline metals. Now, the alkaline metals are most reactive metals group that we have. Very reactive. What do I mean? I mean like bam, like blow up, very easily reactive. They only need to lose one valence electron so that way they can become stable, all of them. And they're highly reactive with water. Do not get them next to water. They're just going to just explode everywhere. All right. The next one, group 2. Let's talk about these groups. Okay, group 2 is the alkaline earth metals. And they are less reactive than group 1. Okay. They have to lose 2 valence electrons. And so because of having to lose 2 versus just 1, that's so quickly, even though 2 is not a lot, it still has to lose 2. It still is less reactive. Okay? So that way it can become stable. Now, group 3 through 12, which is the middle section. Remember, those are the middle ones that we really don't talk about that much. But group 3 through 12 are actually called transitions metals. And they have more than one oxidation number. Okay, remember that oxidation number is the charge. Depending on who they bond with is going to determine their oxidation number. So, you know, gold, silver, some of these weird ones that we have in the middle, copper, okay, zinc, all right, they can have mercury, more than one oxidation number. So, Ms. Munson, how am I going to know? I'm going to teach you how you're going to learn what their oxidation number when it bonds. So depending on who they bond with is going to determine what their oxidation number is going to be. And that is going to be in one of the lessons, but later on. All right, so let's go ahead and talk about group 17. All right, group 17 are called the halogens, and group 18 are called the noble gases. Now, the halogens are the most reactive nonmetals. Right? They need to gain one electron. So who do you think they're going to bond with? They're going to bond with those metals who need to lose one electron. So how easy? I need to lose one. You need to gain one. Bam, we bond together. It's done. Next one here. Noble gases are completely unreactive group. We call them inert. They don't bond. They don't do nothing. Okay? They already have a full valence shell. They are happy. Now, what about those group 13 and 14 and stuff and, and 15 that we didn't talk about, or 16? Those are actually just called the group with the element that's on the top. So for an example, group 13, we didn't talk about that over here because group 13 is just called the boron group. Group 14 is called the oxygen group. Group 15 is called the carbon group, nitrogen group, and oxygen group. That's all they call them. I mean, they don't have different names like halogens and alkaline. They're just called whatever elements up there at the top. So, go back to the previous page, and get out your red, and we're going to label this periodic table. So, I'm going to turn it sideways so I can write a little easier. I'm going to turn it this way. This is called our alkaline metals, right? Group 1. These are alkaline earth metals. Label it on your periodic table. This in the middle is called transition metals. And what makes them special or different is that they have more than one oxidation number. What determines his oxidation number? Who he's going to bond with. And then again, this one's called the boron group, the carbon group, the nitrogen group, the oxygen group. But this one, group 17, is called the halogens. And the last one is called the noble gases. Okay, so make sure you label it. Let's turn the page and let's talk a little bit more. Now, this periodic table that we have and that we currently use is pretty darn awesome. And one of the awesome things is the way that it's ordered and put together not only tells us the number of shells, the number of valence electrons, the number of protons and electrons. There's other things too. So let's go ahead and let's talk about some other things. Now we're going to get to a few things that you may not have talked about before. So let's look at this one. Atomic radii, okay, is the next one. Now the atomic radii is the size of an atom. So when we use the word atomic radii, what are we talking about? We're talking about the size of an atom. They can be small atoms, they can be bigger atoms. Now, I know I'm over-exaggerating because they're so tiny that we can't see them with our eyes. And they're so tiny, we can't even get a regular traditional microscope to look at them. Okay? But they do have different sizes. They can be smaller and bigger. Okay, which element has the largest atomic radii? When we're looking at the atomic radii, we're looking from the center nucleus to the outside valence shell. Okay? That is francium. Has the largest atomic radii. Now, you know, I don't know about you, but there's just some things I just can't memorize. So, to help, we call him Big Frank. Big Frank on the periodic table, because he's big, he has the largest atomic radii, meaning that from the center of the nucleus to the edge of the outer valence shell, he's the biggest one. Okay, where would he be at on the periodic table? Well, I know it's kind of hard because there's nothing labeled here. So let me show you. Here he is right here, francium. So he's actually, go ahead and get your yellow, get your red back out again. Or I guess whatever color you have around you. That is where he's located at. And as we go from left to right on the periodic table, it increases. Oops, I forgot an R. In size. And as we go from the groups from the top to the bottom, it increases also this way. You might see it on the periodic table as a different way. I see some periodic tables, they show it, or they, rather than showing from right to left and from top to bottom, some periodic tables show it this way. Okay? Alright, so some periodic tables do show it this way. Some periodic tables show it from the right to the left and from top to bottom. Either way, you need to know Big Frank is going to have the largest atomic radii. So now let's go ahead and let's look at a few questions that you may have, like test or, quiz. Is lithium or carbon, who has a larger atomic radius? Okay, well, let's look. Here's carbon and here's lithium. Who is going to have the larger atomic radii? It gets larger from here to here. They're on the same row. And as we go down. So since they're on the same row, we don't have to worry about that. So carbon and lithium, who's going to have the larger one? Lithium. Between, where are we at? Ba, beryllium, and magnesium. Who has a larger atomic radii? Magnesium and beryllium. As we go from right to left and from top to down, who has the largest? Ba. Those are going to be questions similar to the quiz and test, okay? The next one, let's talk about this next word, electronegativity. All right, electronegativity. So the word electronegativity means unequal sharing of electrons. So atoms share. Atoms say, I have one extra, you have 7, let me give it to you and we can bond together. Now, when they do that bonding together part, some atoms actually are a little stronger than others, and they can pull the electrons towards them a little bit stronger. What do you mean, for an example? What about H2O? Okay, even though you've never with your eyes seen an actual compound of H2O, you've never seen the H, two H's and one O bonded together, but you've probably seen pictures. And every time you've seen pictures, they probably look like this. H, H, and O. Why is it? Why is it like that? Well, because some of them are stronger than others. So this hydrogen is actually pulling towards the oxygen atom because he's stronger than the hydrogens. Okay, so atoms can physically be stronger and pull more electrons towards them and cause that compound to have what we call different shapes. We'll talk about those shapes later on another unit. So let's look at it. It also measures the atom's ability to steal electrons, right? That's what we're talking about. It's unequally shared. They pull the electrons to them. Sometimes they just steal them. They're that strong. Okay? What is the most electronegative element? He's going to be fluorine. Fluorine is the strongest has the strongest electronegativity. Now, let's look at this chart, because look at this periodic chart now. This one's a little weird. It has the atomic number at the top, it has the element symbol, and then it has all these little weird numbers at the bottom. When we're talking about electronegativity, we must have these numbers with it, because it's really simple math that you have to do so you can see who the stronger one is. But let's go ahead, and I'm going to get my red out. And fluorine is the biggest one, or the strongest one, not biggest. Big Frank, which is francium, is the biggest atom. The strongest atom is fluorine. Well, you know what? Again, I'm not expecting you, and I myself cannot memorize it. So here's a little flossy fluorine. Has the most strength. Okay? So, the closer you are to fluorine, you have a higher electronegativity. The further away from fluorine we go on the periodic table, it becomes and has low electronegativity. Okay? So let's go ahead and look. Where's fluorine? Fluorine's over here. So the closer we go from left to right, it increases in strength. And from the bottom up, it increases in strength. So it can steal or pull electrons towards it stronger. Again, some periodic tables, if you look like on the internet or somewhere else, they may have an arrow that just looks like this. And that works too. From the bottom up, from left to right. Okay? So knowing that, let's go ahead and let's look at some questions that you may have like on a quiz or something like that. So that way we can do that. We can answer that. I'm sorry. Be and oxygen. Be. Where is Be? Here is Be right here, and oxygen's right here. They're both on the same row. Who is going to have a higher electronegativity? Since I don't have to worry about rows, since they're on the same one, I'm just going to go from left to right. That's going to be oxygen. Nitrogen, who's right here, in SB. Where is SB? You might find it faster than I. SB. Okay? So oxygen and SB. Oh, I'm sorry, nitrogen and SB. Who has a higher electronegativity? Well, they so happen to be on the same group. So we're going to go from the bottom up, who is nitrogen. Pretty easy questions. Hopefully it's pretty simple for you and you don't have that much of a problem with it. All right. Let's keep going. Before we keep going, let's talk about one more thing. Let me grab a different one. Let me grab a different color. I'm going to go ahead and mark all of this out. And why am I marking the noble gases out? Do they bond with anybody? No. Why would they? They have a full valence shell. They don't bond. They don't react. They just roam around by themselves all happy. Okay? So, noble gases are not included. Why not? Well, because they're already happy. They're not going to fight and try to steal electrons or pull electrons to them. All right? Let's keep going. The next word. And here's where our numbers are going to come in place. Ionization energy. Okay? So ionization energy is the energy required. Oops, let me turn my notes a little bit. To steal electrons. Right? So we talked about the other word, electronegativity, okay? About unequal sharing of electrons, all right? Kind of like H2O. Now, ionization energy is the energy required to steal electrons, okay, from an atom. So, noble gases have the highest, and here's a shortcut, i.e. ionization energy. Helium, I-U-M, has the highest IE. Now, okay, let me go ahead back and re-say this again. Okay, so first thing is all the noble gases, all of them, are going to have the highest IE. Besides the noble gases, helium has the highest IE. Okay? So, well, why does the noble gases and helium, he lives over there with the noble gases in group 8 or group 18. Why do they have the highest electronegativity or ionization energy? Okay, and if ionization energy is about stealing electrons, I thought that helium and the noble gases are not going to bond with anybody, and they're not going to steal any electrons because they're not going to bond. That's it. Think about it. They are so happy because they already have their valence shell full that they are going to have the strongest energy to hold on to those electrons and not let anyone steal from them. They're not going to steal from anybody, but they're so strong that no one can go and rip their electrons from them. And who do I mean them? Other atoms can't just come over there and just rip argon's electrons away. Argon's too strong. He's not going to let aluminum come and take his electrons. So when it comes down to it, who has the highest IE? Group 18, all of them. Why is that? Well, because no, they don't do any bonding. They don't need to go and steal any electrons, but that's it. They are so strong that no one can steal from them. They are so strong that they hold on to their electrons stronger than any other atoms can. Okay, so let's look at our little periodic table over here. We move from the left to the right to increase. And we move from the bottom to the top to increase. Now again, just like the other ones, right? There's a little thing to memorize it. Is that, where am I at in my notes? Here it is. Here's a little thing to help you memorize it. Hercules helium. Where's helium at? Helium is right over here. Okay, so all of these are strong, but he's very, very strong. He's the strongest of all of them. They're all strong, but he is the strongest of them all. Hercules helium. Which element has the highest IE? Helium does. Well, why is that? If you stop and think about it, helium only has 2 electrons. And so that means he only has 1 valence shell around him. He doesn't have to pull. I mean, imagine if you had both arms out and you had to hold on to something, okay? And you're holding on, and those 2 objects are trying to, not really strong, but they're trying to leave you, but you're holding on. What if you had not just 2, but you had 8 or 10 objects you're having to hold on to, and they're a little further out? They're so far out that you're really stretching both arms. You're strong, but your arms are stretched out all the way, and you're trying to hold on to 8 or 10 things. And you can do it, but it takes a little bit of energy from you. You're strong enough to do it. Wouldn't it be easier for helium, who doesn't have to stretch his arms out too much? Just hold his arms out, and he can tightly grab onto his 2 electrons. But let's go to the next one, neon. Neon has 10 electrons. So that means that his arms are stretched out to hold 10 electrons versus 2. Do you see why helium is the strongest? He only has to hold on to 2. He has to hold on to 10. He has to hold on to 18, 36, 54, and 86. So yes, they're all the strongest. But who is the strongest of the strong? Helium. And that's the reason why. So let's look at this. How about Ca, who is a metal, and Br, who is also over here. So Ca, who is a metal, and then Br, who is a non-metal. How do we go? We move from left to right. So Br would have a stronger ionization energy. What about Na or Cs? Na, who's over here, and Cs. How do we move from the bottom to the top? So Na has a stronger IE. Okay? Again, you might see it on the internet or somewhere else. It looks like this. An arrow that they draw out. Okay? So, who is closest to, who is the closest to helium? Who is the next strongest? Neon, Ne. Who is the furthest from helium? And who is the weakest? Francium. Fr. Okay? But let's go back. Let's think about it. Fr, francium, he has to hold, 87, and he has 7 shells around him. I mean, he's really big and fat. He just doesn't have it in him to hold all those electrons. He's starting to lose. He has 87 electrons. He can't hold on to all of them. You know, they fall away pretty easily. Okay? So let's look at the math. I know I said it on the previous page. I apologize. Here's where we're going to look at it a little bit more. It says here, lithium, Be, and we're looking at period 2. So period 2, which is right here, lithium, Li, Be, boron, B, carbon, nitrogen, oxygen. We're looking at them. Here is their energy. Can you see how their energy increases? 520, 900, and these are kilojoules per mole is their SI unit. 800 kilojoules per mole, 1090 kilojoules per mole. Do you see how it gets stronger and stronger as we move from the periodic table from the left to the right? It gets stronger. It increases. Okay, so they actually do have a number that shows their strength, but it's not on this traditional periodic table. Okay, reactivity. Now the word reactivity refers to how likely an atom is to gain or lose electrons, which depends on how easily they can be gained or lost. Okay, what is the most reactive metal group and why? What is the most reactive non-metal group and why? Okay, so go back to your notes. We have it written down and you can answer those questions. It just says here, as a recap of that new stuff that we talked about, that the largest atomic radii is Big Frank. And if you think about Big Frank, he's got so much shells, he's got so much valence electrons, he got so much electrons that he cannot hold on to them strong. So he's kind of weak when it comes to ionization energy. The highest ionization energy is Hercules, helium. And highest electronegativity is Flossie, fluorine. Alrighty. Other than that, we have this part right here, which we can do in class together. Our notes should be done. And this unit is done. Like I said, this is a quick unit. Alrighty. We will see each other next week. Please make sure you get them done before you come in on Tuesday.